Hello and welcome to my video on Rolle's theorem and the mean value theorem. These are two pretty important theorems in calculus, especially the mean value theorem. It is probably one of the most important theorems in Calc 1. So our objectives today are first to understand and use Rolle's theorem, and number two, to understand and use the mean value theorem. We'll start out by looking at Rolle's theorem, and then we'll go to the mean value theorem. We'll show some examples and look at what some of the pitfalls on these problems could be. With Rolle's theorem, we're going to let f of x be continuous on the closed interval from a to b and differentiable on the open interval from a to b. Please note that it's differentiable on that open interval, so we're not necessarily looking at the endpoints there. If f of a equals f of b, then there is at least one number c in the interval from a to b such that f prime of c is equal to 0. Okay, this Rolle's theorem will give conditions which guarantee that the existence of an extrema inside of a closed interval. You must have the fact that f of a equals f of b on that closed interval. So one of the things you're going to have to do is you're going to have to check to make sure that that is actually the case. The other thing you have to be aware of is that it does have to be differentiable on a to b, on the open interval from a to b. That eliminates the possibility of a cusp or some discontinuity too. So make sure you look and see that it is differentiable and that it is continuous, and then Rolle's theorem will apply. Here's a graph that will kind of illustrate Rolle's theorem. So what happens on this is we have a function that is differentiable and continuous on the intervals from a to b. You'll notice that at f of a and f of b are both equal to this number d, so they are equal. And what Rolle's theorem says, as long as a function is continuous and differentiable, that it has to start at a, it's got to come and it's got to eventually level off and come right back down to b. Again, this is due to the fact that it is continuous and differentiable. So therefore, since it's continuous, there's no break. And since it's differentiable, it must be a smooth curve. And therefore, since it must be a smooth curve without a break, somewhere between a and b, there has to be this number c where our function is going to have a horizontal tangent. Again, you got to keep in mind some of the musts. It must have continuity and it must have differentiability on that open interval. Now let's look at an example using Rolle's theorem. In this case, we have a function f of x, which equals x minus 4, that quantity, times the quantity of x plus 2, that quantity squared, on the closed interval from -2 to 4. Okay, so first thing we have to do is check to see, can we actually apply Rolle's theorem? So the first thing I check for is, just real quick, is at the endpoint, is f of -2 equal to f of 4? And by quick inspection, we can see that both f of -2 and f of 4 are both equal to 0, so that condition on Rolle's theorem is satisfied. The other thing we have to check on is this function continuous, and is it continuous and differentiable on the open interval from -2 to 4? In this case, we are dealing with a polynomial, and polynomials are continuous and differentiable everywhere, so that condition is also satisfied. So therefore, I do know I can apply Rolle's theorem, and so I know that somewhere between -2 and 4, there is a number c such that f prime of c is going to equal 0. So what I'm going to have to do to find that c is I'm going to have to take the derivative. So using the product rule on this, the derivative of the first is 1 times the second, which is x plus 2, that quantity squared, plus the first, x minus 4, times the derivative of the second, which is going to be 2 times x plus 2 times 1. 1 is the derivative of that inside function. Simplifying that a little bit, I get the x plus 2 quantity squared plus 2 times x minus 4 times x plus 2. Now to go through and find where we have our critical numbers, where the first derivative is going to be 0, I need to factor that. And I notice that there is a common factor of x plus 2. So I will pull out the factor of x plus 2, and I'm left with x plus 2 plus 2 times x minus 4. And when I simplify that inside the brackets, I will get 3x minus 6. So f prime of x is x plus 2 times 3x minus 6. Real quick, we can take a look at that, and we should be able to recognize that this first derivative is going to be 0 when x equals negative 2, because negative 2 will make this first factor equal to 0. And when x equals 2, because x equals 2 will make this second factor equal to 0. So those are our two values that we're working with on this one. Now the condition that we have to keep in mind though is that this problem says, it says that somewhere between, that there is a number c inside the open interval from negative 2 to 4. There's only one of these values that actually satisfies that. It could actually be in the open interval from negative 2 to 4, and that would have to be 2. So in this case, f prime, we know f prime of 2 is the value that satisfies Rolle's theorem such that f prime of 2 will equal 0. So our c value in this case for Rolle's theorem is 2. Another one I want you to look at, kind of a quick one, is g of x equals x squared minus 1 over x on the closed interval from negative 1 to 1. Again, a very quick inspection tells us that g of negative 1 and g of 1 are both equal to 0. So I know g of negative 1 equals 0, and I know g of 1 equals 0. So that's okay. But can we apply Rolle's theorem? And the answer on this one is no. This function is not continuous and differentiable. It's not continuous on the open interval from negative 1 to 1 because we have an x in the denominator. So 0 is part of this interval, and this function is not defined at 0. So in this case right here, Rolle's theorem cannot be applied. You need to go through and, as you're working on these problems, identify those. Look for the ways that the theorem actually could fail. Remember, it must be continuous on the closed interval and differentiable on that open interval. Now let's look at the mean value theorem. Again, this is one of the most important theorems in calculus. It's really closely related to what's called the fundamental theorem of calculus that we'll be doing in Chapter 4. The fundamental theorem of calculus actually ties both the two main branches of calculus together. So here's our mean value theorem. If f of x is continuous on that closed interval from a to b, so this is going to sound a little bit like Rolle's. It's continuous on the closed interval from a to b and differentiable on the open interval from a to b. Then there exists a number c in a and b such that f prime of c is equal to f of b minus f of a over b minus a. In other words, that the slope of the tangent line at x equals c is going to be equal to the slope of the secant line that connects 2 points on the curve, the 2 points at the end point of our interval that we're working with. Let's look at this graphically. This is the mean value theorem graphically. What we see here is I have two values, a and b. I've just arbitrarily placed them there. And they connect. Here's our curve, f of x. And this is the secant line that connects the 2 points, a f of a and b f of b. That secant line has a slope. And according to the mean value theorem, if this is a smooth, continuous curve, again, it must be a smooth curve. Cannot be a cusp because a cusp is not differentiable. We must be differentiable on the open interval, which means we have to have a smooth curve. That there must be a value c such that the tangent line, which I've drawn here at x equals c to our curve, is parallel to that secant line. The secant line that connects a f of a and b f of b. That's what the mean value theorem tells us must be true. Now let's look at an example involving the mean value theorem. In this case, f of x is going to be the square root of 2 minus x on the closed interval from negative 7 to 2. So the first thing I have to do is determine, is this thing continuous and differentiable on that interval? And in this case, it is. We know that the domain of f of x is all values of x that are going to be less than or equal to 2. so that all these values in our interval do fall within that domain. So this is a continuous and differentiable function on that interval. So what I have to do now is I went through, and you want to find the function's value at each endpoint of the interval. So f of negative 7 comes out to be the square root of 2 plus 7, which will be square root of 9, which is 3. And f of 2, well, if I plug 2 into x there, I'm going to get the square root of 0, so that's 0. So I know that I have these 2 points here. The 2 points are negative 7, 3, and 2, 0. And so what I want to do is I'm going to go through, find the slope of the line that connects those 2 points. And so I did 0 minus 3 over 2 minus a negative 7, which gives me negative 3 over 9, which reduces to negative 1/3. So since we can apply the mean value theorem, it is continuous and differentiable. It's continuous on the closed interval, differentiable on the open interval. So I know there has to be a number c such that f prime of c is going to equal negative 1/3. So what I do is take the derivative. So when I took the derivative of that, I got 1/2 times 2 minus x to the negative 1/2 times a negative 1. Don't forget the chain rule on here. So that becomes negative 1/2 times 2 minus x to the negative 1/2. And I'm going to set that equal to negative 1/3. And I'm just going to solve it for x. Now some people will go, I didn't do it on this one, but sometimes people like to do this. Instead of going through and having this be x, because we want to find the number c, they'll replace the x with a c. But it doesn't make a difference. It's not going to cause you a problem as you progress through these problems if you keep it as an x. But if you want to make it a c, go ahead. So right now, what I did at this point, to go from here to here, what I did is I just rewrote the problem. I said 2 minus x to the negative 1/2. I made that as negative 1 over 2 times the square root of 2 minus x. So that I made that square root in the denominator of the fraction, and that equals negative 1/3. Because both are negative, I can cancel out the negative signs, and both fractions, I have 2 fractions equal to each other, so I know their reciprocals must be equal as well. So therefore, I can say 2 times the square root of 2 minus x is equal to 3. Dividing both sides by 2, I get the square root of 2 minus x equals 3 over 2. I square both sides, I get 2 minus x is equal to 9/4. Subtracting 2, I get the opposite of x, or negative x if you want, equals 9 over 4 minus 2 over 1. Getting a common denominator, I'm going to get that the opposite of x is equal to 1/4. 9 over 4 minus 2 over 1 will equal 1/4. And therefore, I can say that x equals negative 1/4. So our answer on this one, the c value that's in the interval from negative 7 to 2, that guarantees it will be the place where the curve will have a slope parallel to the secant line is at negative 1/4. So that's the value that satisfies the mean value theorem. This now concludes the video for Rolle's theorem and the mean value theorem. Please make sure to go and look over the conditions, and remember that you will need to verify that the conditions do hold for each problem when you are applying Rolle's theorem or the mean value theorem. So with that, what we'll do is you do not need to complete a whisk on this one. We will just check your notes at the beginning of class, and we'll see you in class. Have a good evening and good luck.